Welcome nerds, HornCode here again, just your average coding little devil. Back here again to explain to you geeks the most common coding interview questions that the big tech nerd companies love to ask. And yes, even though knowing how to solve this kind of coding questions aren't as useful in real life as diplomacy is with Vladimir Putin, we still need to know how to solve these kinds of questions, especially if we want to get into that big tech money pie. In today's video, we will be discussing a problem involving the binary search tree. The data structure, that is, not an actual tree like the ones that are burning out in California. Now into the serious but boring part of the video, the problem description. Given the root of a binary tree, determine if it is a valid binary search tree. A valid binary search tree is defined as follows. The left subtree of a node contains only nodes with key values less than the main node's key value. The right subtree of a node contains only nodes with the keys greater than the node's key value. And both the left and right subtrees must also be binary search trees. So in the case of example 1, this is a valid binary search tree because the left node's key value is less than the main node's value, and the right node key value is more than the center node value. And example 2, this is not a valid binary search tree because for here, the right node's value is less than the center node value, which is 5. Now, just a reminder on what a binary tree data structure usually contains, which is the following. It's basically just an object node which has a value data property to store its value, a left pointer property which will be a pointer to the node that's on its left, and a right pointer property which will be a pointer to the node that's on its right. Quite simple, right nerds? Now, there are several ways to solve this problem, but here we will be using one of the binary search tree traversal methods, specifically the recursive depth first search in order traversal method. Depth first search in order traversal method. Quite a sexy name, but it's sexy in dyslexia. So the reason that we will use the recursive in order traversal is because when we traverse a binary search tree in the in order way, we traverse all numbers in an ascending order fashion. So this way, while we in order traverse the tree, we can store all our traversed nodes and check that each element that we traverse is actually bigger than the previous one we traversed. Now let's go into the graphical overview of a in-order traversal function of a binary search tree. So first we have here on our left a binary search tree, and here on our right part of the screen we have a code of a normal recursive in-order function traversal method. You know, it saddens me how many interviewees get torn apart by something as simple as recursion. So next, we will go through the recursion process step by step. So first, we call the in-order function with the root node of the binary search tree, in this case being node 4. Then we recursively call our function with the left node of this root, in this case being node 2. After that, since we already are in a recursive function, we now call it with the left pointer of this node, which is node 1. So then here we have no more left nodes, so we print our node value 1, or in this case push it into the traversed nodes array. Then we continue with the function. It is asking to traverse the right node, but since we do not have a right node, we finish with this node's function call. And since we have some previous recursive calls on the stack, we will automatically be called to our previous function of call node of node 2. Here on node 2, we have already called node left, so now it's time to push the node value 2 to our traversed nodes array. And then call its next step in the recursive function, which is to call the function on right node, which is node 3. On our node 3, we do not have a left node, so we push the value 3 to our array. Then we do not have a right node, so we go back to our previously called recursive function on our stack, which is the one called on node 2. On node 2, we have finished calling our right node, so now here we have to exit to our previously recursive function, which is the one on node 4. On node 4, we have already called left node, so now it's time to push the node value 4 to a traverse nodes array. Then our next step is to call the right pointer of node 4, which is node 6. On node 6, we do have a left node, so we call our net load of node 6, which is node 5. On node 5, we do not have a left node, so we push the value of node 5. Then we do not have a right node, so we exit to the previously function call stack, which is node 6. Here on node 6, since we already traversed node left, we push our value on node 6. Then the next and final step is to call our node right of node 6, which is node 7. On node 7, we do not have a left node, so we push our node 7's value to the traverse node. And we do not have a right pointer to node 7, so we exit all function calls. And as a final result, we have all the sorted numbers. So now all we have to do is check that the numbers on the array are actually sorted or in an ascending value. If they are in ascending value, then we do have a binary search tree. If they are not in an ascending value, then it is not a valid binary search tree.
You know, it also saddens me how many families can be torn apart by something as simple as wild dogs. So now here into our function, the first thing that we have to do is declare the array that we will use to store the traversed values. Then we have to add our recursive traversal function, the in-order recursive traversal function, just as we saw in our conceptual overview. So on our function, we first traverse our left side of the node. Then after traversing all the left side of the node, we will push our value on our array, and then we'll traverse our right part of the node. Then we should need to call our in-order function so we can populate our array. And after that, we'll just have to check if the array is sorted. We can do that by traversing the node and checking if the current value is smaller than the previous value, the next value. So we can do this with the loop, and then just check it. If the current value is bigger than the next value, then that would not be a valid binary search tree. If it is, then we'll just return a true. So let's run this. Oh, I made a mistake. The devil makes mistakes. Let's see what I did wrong. Oh, this should be like this. Sorry about that. The devil makes mistakes. And yeah, here we go. Very easy now. So please subscribe to this YouTube channel or follow me on HornCode.com, because every now and then I might be posting another one of these video experiences.